Pika?
Oh no!
Welcome back. In this video, we will first find the definition of the derivative using our knowledge of limits. Second, use the definition of the derivative to find the derivative of x squared. And third, we'll enjoy watching an otter playing basketball. In order to discuss the definition of the derivative, we need to return to our discussion about slope. Let's say you were having this function and you wanted to find the slope of the secant line between some value. Let's just put a random point here. Let's call it x1. And then the point on the graph that corresponds to that would be f of x1. When you plug in x1, you're here on the graph. And you wanted to find the average slope between this point and some other point further down the line. We'll call this x1 plus h. And what that really means is the distance from here to here is h. So if this is a distance of x1, then this is a distance of x1 plus some arbitrary amount h. And then correspondingly on the graph, this is where you would be on the graph if you plugged in x1 plus h. To find the slope of the secant line, or the average rate of change between those 2 points, you'd use the formula that we've already been practicing for finding the slope of the secant line. You would do the final function value, in this case that's f of x1 plus h, minus the initial function value, in this case that's at just x1, and you divide that by the difference in x values, so x1 plus h, subtracting just x1. And all this is change in y over change in x, like you've been used to doing to finding the slope of the secant line. Okay? We're going to simplify this a bit. The top's going to stay the same. It's just f of x1 plus h minus f of x1. But on the bottom, the x1 will subtract another x1, and we're just left with h. So this would be the slope of the secant line between these 2 points on our graph. As we've already said, h is the difference in x value between x1 and then x1 plus h. So what if we made the distance between these 2 points as small as possible? If we could, we wouldn't be finding the average slope anymore. We'd be finding the instantaneous rate of change, or the slope directly at that value. So imagine that this h becomes smaller. The distance between these 2 points becomes smaller and smaller and smaller. These points get closer and closer together, and we'll eventually get the exact slope at the point we care about. And this leads us to our definition of the derivative, which we set up using a limit. We say, okay, let's imagine our limit h heads towards 0, so the distance between those 2 points is heading towards 0. They get closer and closer together, and we'll keep our slope the same. So all the derivative is just the slope, but assuming you get 2 points that you're finding the slope for as close to each other as possible, as the distance between them heads towards 0. I'd like you to put 3 boxes, or a bunch of boxes, around this formula. So when I check it in your notes, I'll see it. This is the huge formula that we're going to need. This is, and I said 3, so I'm going to go ahead and do 3 here. This is our definition of the derivative. We're going to keep coming back to this definition. So this is the definition of the derivative. Let's try to use our definition of the derivative to find the derivative for the function f of x equals x squared. So this is our function, and our question is, what is f prime of x, or what is the derivative of f of x? Well, in order to do this, we'll use our definition of the derivative, which we've already stated in this video to be f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. In the last part of the video, I put x1 and x1 here, but it doesn't really matter. We can just write x plus h. It's just some random number x and then some random distance h. So we'll use the definition of the derivative. We say the derivative is equal to this. But how does that work? We need to actually plug in some values here from our function x squared in order to use this definition. The first thing we need to do is we really have to lock down what f of x plus h is. We know what f of x is. It says right here, it's just x squared. We have to lock down what this f of x plus h is. So let's go ahead and do that over here. Let's say f of x plus h. And all that really means is plug in x plus h to the function f of x. So we're going to plug in x plus h to the function f of x. It replaces the x, and it's still squared because you just plug it in for this x plus h, and then the squared will stay there. In order to evaluate this, we'll write this out. We'll extend it out to x plus h times x plus h. When we FOIL this out, we'll get x squared plus 2xh plus h squared. Now we know what f of x plus h is, so we can continue our problem. Let me make some space over here. So we can now replace some stuff. We say the limit of h approaches 0 as h gets smaller and smaller, the distance between our 2 points. F of x plus h is x squared plus 2xh plus h squared. That got subbed in here. And then minus f of x. F of x, like we said, is just x squared all over h. Now, at this point, you might be thinking, let's use direct substitution to evaluate this limit, and you can plug in 0 to this function for h. But if you plug in 0, this will be 0, this will be 0, this will be 0, and these x squareds will actually subtract each other, so you're going to get 0 over 0. So we need to simplify this a little bit more before we use our direct substitution. Limit as h approaches 0. X squared minus x squared is canceled out, and we have 2xh plus h squared over h. We can cancel one h from each of these terms. We'll take care of the squared here. And so we'll get the limit as h approaches 0 of 2x plus h. And at this point, we can apply direct substitution. We can plug in 0 for h. So this will just be 2x plus 0. We get our answer as 2x. So we can finally go back and answer the question, what is f prime of x, or what's the derivative of this function? We know now that the derivative of this function is 2x.